Now that we have learned about the quantum numbers, which are N, L, ML, and MS numbers, now we're going to learn about how to fill those electrons in the atom, one by one, okay, shell by shell. So as we learned about N is equal to 1, N is equal to 2, N is equal to 3, we are going to learn about what it all means. So just to review then, we know that electrons exist in very specific locations, which are the N number, the L number, the angular momentum, the ML number, and then the magnetic spin number, which is the MS. So in this chapter now, we're going to learn about how to specifically fill those electrons in those locations. What you will also learn is that each electron has its own particular address, okay, which means that no two electrons can have the same quantum number. We learned that before also, and we're going to emphasize that again this time. So we'll learn how to fill electrons. And the way we fill electrons are in two different ways. One is called the electronic configuration, which is the SPDF notation. Remember the SPDF, that's coming from the angular momentum, which is the L number. And 0 was S, 1 was P, 3 was D, and F was 4. So that's the SPDF notation. And then there's something also called the box configuration or the orbital diagram. And in this case, electrons are shown as arrows. And this gets a little bit even more specific than the electronic configuration. By the time we fill out the box configuration, we know exactly how these electrons are in the atom. So there are three principles for filling out electrons, and these are just rules. And you will learn that as we go on, you will internalize these rules without even realizing that you are actually following these rules because they make perfect sense. Okay, so for example, Pauli's exclusion principle, no two electrons can have the same quantum number. You will learn that as we go on, you cannot fill any electron that is not supposed to be there. Okay, so as we do that, you will realize that you're just doing it, okay, without even knowing that this was Pauli's exclusion principle. Then there is the Aufbau principle, which is building up the electronic configuration using ground state energy, which really just means that you fill the lower energy electrons first, and then you go on to fill the higher energy electrons. So that's the Aufbau principle. And then again, as we start filling out electrons, you will see that it is pretty easy to do then. And then there's the Hund's rule. And Hund's rule is more specific when we start filling out box configuration, not so much when we do the SPDF notation. Okay, but when we get to the box configuration, then we learn that electrons should be filled singly, okay, in the subshells. The subshells are the SPDF, and then we pair them up, okay, according to the magnetic spin numbers. So we will deal with that when we get to it. What I have done for you here is filled out the electrons for the first three rows. Okay, so you can see here for hydrogen, it is going to be 1s1. 1 is the principal quantum number, and then S is the first subshell in it. And then because hydrogen has one electron, you put 1. This 1 is written as a superscript, not along with the line. Then helium, 2 electrons, still the first shell. Now still S, because S can have up to 2 electrons, and then 2 electrons over here. Going on to the second row, we have lithium, which has 3 electrons. So because it has 3 electrons, you still have to fill out the first shell, which is the 1n, and then the S electrons in it, which can have 2 electrons, and then you go on to S1. Beryllium, again, you have to fill out the first one, which is beryllium has 4 electrons, so you fill out the 1s2, then you go on to the second shell and fill 2 electrons more in the S. When you get to boron, now you have 5 electrons, and now the 5th electron is going to go into the P subshell because the first 2 S's are all full. Carbon, the first 2 S's are still full, so going on into P. So nitrogen, oxygen, fluorine, neon, they will all fill electrons in the P subshell because P can have up to 6 electrons, all right? And so the S's are filled over here. When we get to row number 3, then we have 1s2, sodium, which has 11 electrons, 2s2, 2p6, and then 3s1. So now we fill out the third shell because the first 2 are filled up. with 2 electrons and then 8 electrons, and then the third one can take 1 electron. Magnesium, same thing, and then again the last subshell will get 2 electrons, which is S, and then once S is filled up, then when it comes to the next element, which is aluminum, then you start filling out the P subshell. So this is how the filling of electron go. These ones, I need you to look at all of this so that you can see a trend in here, okay, which I will talk about a little bit later, because as you can see over here also with lithium and sodium side by side, that they're both ending in S1, which is group 1, and then beryllium, which is group 2, is ending in S2, and then starting with boron and aluminum, which are in the same group, are ending in P1. So note this little trend here, and we'll talk about it more later. So I mentioned to you that you have to fill electrons according to Aufbau principle, which is according to the energy level. So how do you know what energy level we are talking about? Okay, so some of it is pretty straightforward. So for example, in n numbers. Okay, so this is the n number, which is the 1, 2, 3, 4. In case of n numbers, 1 is lower in energy than 2, then 3. So which means 1 is the lowest, and as you get to higher numbers, it gets to higher energy level. Within the same shell, okay, which means if you're talking about S, P, D, and so on, then S is lowest in energy, then you go on to higher level with B and then with D, okay, and so this is the energy level when you fill electrons there. Within the P, everything is equal in energy. Now remember, P is coming from L is equal to 1. So you have three different orientations, -1, 0, and +1. So if you have these three orientations, all three of them are the same energy level. Okay, and that's called degenerate, all right, which is right here for you. It's called degenerate, which means it's the same energy orbital. So the 2 electrons that you find in S, they are degenerate. The 6 electrons you find in P are degenerate. The 10 electrons that you find in D are degenerate, which means that they are the same energy level no matter which one you start with. However, 2p is lower than 3p because this is in the second shell and 3p is in the third shell. Okay, so don't compare between those two shells, but if you do, then you know which one is higher now. But within 3p, all the p electrons are the same energy level. Okay. All right, so there are two ways of filling out electronic configurations regarding the energy level. One is using this chart, okay, that's over here, which you can use definitely. And the other one is using the periodic table, which I'm going to do with you in class, okay, and probably we'll go through it a little bit more thoroughly as far as how to fill electrons there. So for you, it is better to use the periodic table because that's what you will have in the exam also. You will not have this chart in the exam, but I will tell you how to use this chart, okay, in case you find this one more convenient. And it's very easy to write out, okay, so you fill out, you write all the shells that are possible, okay, and then expand on that. So for example, the first shell has only one S, the second one has 2S and 2P, the third one has 3S, 3P, 3D. So you write everything horizontally first, and then you use the arrows to fill out electrons. This takes a little bit more time than what we do with the periodic table. Okay, so in class, I'm going to teach you how to use this with the periodic table, and you will see it goes a lot smoother, okay, with that. But anyhow, let's go over this one really quick. Okay, so you fill out the 1s first, you follow the arrows, okay, pretty much that's all you're doing in this case. Okay, so this is the first shell that you fill out, then you fill the second shell with the 2s, the second shell with 2p, then you get to the third shell and you fill the 3s, and then you fill the 3p. But then after 3p, you don't fill the 3d, you actually go down to 4s, okay? And 4s is in the next shell over. And after filling 4s, you actually go back into the third shell, fill the 3d, then you come out again, fill the 4p, then go out all the way out, okay, to fill 5s, come back in, fill the 4d, we haven't even touched the 4f yet, okay, so fill the 4d, 5p, 6s. So by the time you're in 6s, then you come back and fill the 4f. Okay, and so this is how your arrows go. Okay, and this is how the energy level goes. Now again, remember, these are all calculated numbers, but this is how it is also. It's not just a calculation. This is how electrons are, because we know how atoms behave, okay, chemically speaking. So we know that this is how electrons are filled in any kind of an atom. Okay, so this is not just hypothetical. All right, this is for real. So this is how you fill the shells out according to the energy level. Okay, and so this here, right here, on the left, it shows you how these things are filled out. So 1s, 2s, 2p, 3s, 3p, 4s, and then back to 3D again, 4p, and then 5s going outside, going inside, going outside, and then outside. Okay, so follow these arrows. That's what you have to do in order to use this chart. The box configuration. This is similar to the SPDF notation. In fact, I would suggest that you always write the SPDF notation before starting to fill the orbital diagram or the box configuration, because you need to still know how many electrons to place, and you still need to write down the electronic configuration. So you might as well just fill it out anyway. Okay, so here it goes. For helium, which has 2 electrons in it, this is how you would fill out the electrons. Okay, so you fill out the arrow going up, and you have the arrow going in the opposite direction. In the box configuration, now we have to start using the last quantum number, which is ms number. In ms number, we learned about the fact that electrons can have 2 spins, plus half and minus half. So one of these spins is plus half, the other one is minus half. And you can see that the plus and the minus half, or the ms number, has nothing to do with the shell number. It has to do with where and which subshell you're filling electrons in. You can use full arrows or half arrows. Okay, this is called a half arrow. A full arrow would be just like we have in any kind of an equation. So you can use either one of those. I have used both in this PowerPoint. So in this particular slide, I have only one kind, but another one, I may have a different one. So you can use both. It doesn't matter to me which one you use, provided that the electrons are going in opposite spins where they're supposed to. So in case of helium, which is 1s2, you have these 2 electrons filled in opposite directions. For lithium, which is 1s2 and 2s1, you fill out the 1s, again with the 2 electrons going in opposite directions, and then 2s, which has only 1 electron. Now you can draw this going up if you want, or going down. It really doesn't matter. When you get to carbon, which is 1s2, 2s2, 2p2, now you have the 1s, which has the 2 electrons, again opposite spin, 2s, again opposite spin. But now when we get to carbon, now we have these 2 electrons going in 2 different orbitals, okay, or 2 different locations, because as we learned from Hund's rule, is that we have to fill the electrons singly first before we can start pairing them up. Okay, so instead of drawing the 2 electrons in the same square, we have to actually draw them in separate shells, okay, or excuse me, separate subshells. So that's why you see these 2 electrons over here. Going on to nitrogen after carbon, which has 7 electrons, which has 3p electrons. Each electron is filled singly first. Then when you get to oxygen, which has 8 electrons, now you can start pairing electrons up. Okay, so up to 3 electrons in the 2p, you have to fill them out singly. Okay, and then you start pairing them up when you get to oxygen. Then fluorine, which is 9 electrons, has p5. 5 electrons in the p subshell. Now you have 2 paired and 1 unpaired electron, and in neon everything is paired up. Okay, so in case of nitrogen, you have 3 unpaired electrons. Now it is a good idea to put all of these electrons in the same spin. Do not put one electron going up and the other one going down. That's not a good idea. Make sure that all the electrons are going in the same spin. When you start pairing them up, then you start putting them in opposite spin in the same box. Okay, but the other 2 electrons, they should still be going in the same spin. So that's the rule for drawing box configuration. Now the other thing I want to point out before I move ahead from here is the fact that there is one box for S, one box here again for S, but the P here is a big rectangle which is then divided 3. Okay, and this, remember, is -1, 0, +1, because in P you have 3 orientations. So by the time you get to D, you will have 5 sections, okay, in one big rectangle. So here are some more examples of electronic configurations, and here we have both. Okay, we have the SPDF notation and we also have the box configuration filled out. Now in this case, as I said to you, these are full arrows, and this is also allowed and the previous one was also allowed. So you can do whichever one you want. Okay, it doesn't really matter. But anyhow, here is calcium. And calcium has 20 electrons, so 1s2, 2s2, 2p6, 3s2, 3p6, and you go on to 4s2. The easiest way to know if you filled out all the electrons is go ahead and count all the electrons, okay, on the top. So count all the superscripts that you have. And so 2, 2, and 6, and that's 10 electrons. And then here are the next 10 electrons, okay, which gives you a total of 20 electrons. So that's how you keep a track of your electrons. And again, make sure that you write everything in increasing energy. Okay, this is the box configuration for calcium. Since you have 20 electrons, everything is paired up. Okay, and so 1s2, 2s2, 2p6 over here, all the 6 electrons are paired up and in opposite spin. And then we have the 3s2, the 3p6, and then the 4s2. Okay, here this is zinc, not zinc, bromine, and bromine is 35. And so now we have 1s2, 2s2, 2p6, and all of this wonderful things. Now we also have d electrons here. Okay, so 3d10. So remember how we had to do this. We have 3s2, 3p6, and then we go out to fill the 4s2 electrons, and then we come back in to fill the 3d electrons, and then we go out again to fill the 4p. So again, look at the chart that we had with the arrows to talk about the energy levels. Okay, so hence that's why you have this 3d over here after 4, because we had to go inside. And I would suggest this is how you write out your configuration. Just because this is 3d does not mean you should write it over here along with the other 3s. You should write it according to the energy level. Okay, so the 4s2 is lower in energy, so you write the 4s2 first and then the 3d. Okay, and then we have the 4p5, and then here is the box configuration. And as you can see, since we're dealing with 35 electrons, we have a whole bunch to fill out. Okay, so this is a little time consuming. It's not hard, it's just time consuming. So when you get to 4p5, since we have unpaired electrons, we have one electron that is left by itself. Okay, and then here is iron, and iron is 26 electrons, and now we have to stop at 3d. Okay, so we fill the 4s2 and then 3d, and in iron you have 6 electrons, so one is paired, the other 4 are not paired then. Okay, so that's how you fill out electronic configurations. There are a couple exceptions that we have for filling out orbitals. You will see that in chemistry we have almost everything, pretty much by the rules, but sometimes there are some exceptions. Okay, and in this case also you already know about one exception. Okay, and that was the energy rule, and the energy was that you fill out the lower energy level first. So even though you're not filling out according to the shells, you're filling out according to energy, and for that reason you're filling out 4s before you fill out the 3d. Okay, and that is an exception, because technically speaking, I mean, if you're in the third shell, you should fill the third shell completely before going on to 4. All right, so that is what anybody would think, but that doesn't really quite happen. Okay, so that is one exception which we have already learned when we were filling out the configurations. The second one that we have is specifically for the transition metals. Okay, now transition metals can have up to 10 electrons in there. Okay, that's the D subshell, so you can have up to 10. So the first exception is for the fourth column, which is chromium column. All right, and so it goes for the chromium and the entire column below it. And so chromium should be 4s2 3d4. Okay, because it's in the fourth column, so you should have 4 d electrons. But it turns out that it's actually 4s1 3d5, which means that one electron from the s has gone into d. Okay, and so what happens then is now D is half filled. D can have up to 10 electrons, but now D has 5 electrons, whereas S has 1 electron. So if you think about it, this is kind of interesting, because now for S and D, everything is singly filled, all right, which means everything is unpaired, which is a lot more stable than S2, this being paired, and then D with only 4 electrons in it. Okay, and so now with D is half filled, all singly filled electrons, and then S will give 1 electron to the D to make that happen. And this is just because it leads to more stability. Okay, that's all there is to it. So it will happen in all the elements below chromium. So molybdenum should also have the same kind of an exception, okay, for this. The second exception that occurs is for copper, which is the 9th column. And in this case, we have the same problem because D is going to have 9 electrons in it. Okay, it's going to be a lot more stable if it has 10 electrons in it, which are all going to be now paired electrons. So again, it will take 1 electron from the S and put it into the D. All right, and therefore 4s1 3d10 is what the configuration is for copper and all the elements below it. Okay, and so this leads again to more stability. That's the only reason why this kind of a thing happens. But you have to remember these exceptions, because this is really how it is. It is not the way you would logically think it should be, but we have to think in terms of atomic stability and all that, and therefore this is the exceptions that actually occur. So here's the periodic table, all right, and let me classify this again for you a little bit. If you remember, we've learned some of the names before. So for example, group 1 is considered to be the alkali metal, group 2 is alkaline earth, and so on and so forth. But now we're going to divide it according to electronic configuration, all right, and according to how you fill electrons in the elements, the first two groups are called the S block, okay, because remember S can have only 2 electrons in it. So group number 1 and group number 2, these can take S electrons, so this is called the S block. Group number 3 to group number 8, okay, they can have up to 6 electrons in it, and this is the P block then, okay, because this is where you're filling in all the P electrons. Helium is a little bit out of place here because helium, you're still filling the 1s electrons. Okay, so that should actually belong in the S block. Then here are the transition metals. And the transition metals, there are 10 columns. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so you can have up to 10 electrons. And this is called the D block then. From the middle over here, we have the F blocks. Okay, and F blocks, F can have up to 14 electrons, because remember F was coming from 4, and 4 can have from 3, excuse me, and so it can have 7 different orientations. Okay, and so therefore you have 14 electrons in the F block, and so currently we have 2 of the F blocks, so 4F and 5F. There are not enough elements in the world, in the universe, to have a 6F or a 7F yet. Okay, so this is where we are right now, and this is how the periodic table is divided according to different blocks from the electronic configuration. And here's the electronic configuration. You may want to keep this handy for a while, but of course you can't use this on an exam, so you need to understand this. Okay, so the first block here, remember these two are the S block, and in case of the first block, you can see that, or in the first group, all the elements are ending in S1, S1, and S1. Okay, because there's only 1 electron, okay, for that group. For group number 2, everything is ending in 2 electrons, okay, which is from S. Then you come to group number 3. Now S is already filled up, so now you start filling with P, and so then P is all 1, 1, 1, 1, 1, and then this carbon group is P2, the nitrogen group is P3, P4, P5, P6. Okay, that's how it goes. And then here we have the D block. In case of D block, there is D1, D2, D3, Now there is no D4. We talked about that just now with the exception. So there is no D4. There are two D5s. Okay, in one case you have the 4s1 and 3D5. In the other case you have the traditional 4s2 and 3D5. Then D6, 7, 8, and again remember there is no 3D9 because it is 4s1, 3D10, and then here is the 4s2, 3D10. And that is how the electronic configuration is if you follow the if you follow the columns. The only thing that changes as you go down any kind of a column is the shell number. So for example, for boron, the shell number is 2. For aluminum, the shell number is 3, and then 4 and 5 and so on. Okay, so the shell numbers are also given to you here on the left hand side. So group number row number 1 is shell number 1, row number 2 is shell number 2, row number 3 is shell number 3, okay, and so on. This is how it kind of goes. Now a little bit later I'm going to go ahead and fill this out for you according to the periodic table. Okay, so for example, we can pick a random element and then try and fill it out. Okay, but this is how the periodic table is. Now, one thing I want to show you here real quick before we go on is in the third row, which has 3s, 3p, and 3d. You can see you have the 3s, there is the 3p, but there is no 3d, and that's because the 3d is actually down here. Okay, why is it down here? Is because we fill 3d after we fill 4s. Okay, so we have the 4s and then we have the 3d, then we come out again to 4. And how do we know this is 4? This is because helium is shell number 1, neon is shell number 2, argon is shell number 3, and so by the time you get to this row here with krypton, this is shell number 4. Okay, so as we say, the transition metals are kind of sunken, okay, a little bit. They are below the third shell, all right, just below it. So you go out to 4, go into 3, you go out to 5, and then you go inside to 4D. You're in the 6th shell over here with cesium and barium. But when you fill out lanthanum, from 6s you go to 5d. Okay, that's how it goes. And see over here, you're going to 4f, which is even over here, which is even before that. Okay, so because of energy considerations, we have these little things, but the periodic table really helps out because the periodic table is actually arranged according to the energy levels. So if you follow the periodic table, you cannot go wrong. All right. So let's take an example of iodine and try to fill it out according to the periodic table. Okay, as I will show you more in class also, but I thought I'll do an example here as well. So here we have iodine, which is 53 electrons. And if you think about it, 53 is a lot of electrons, okay, to fill out, but not if you know how to fill according to the periodic table. All right, so stay with me and we'll go through it one by one. All right, so you have to start from the first shell, okay, over here. So you start with 1s2, that is your first shell. Then you fill in the 2s2, which is this s block over here. Then in the second shell you still have the p electrons, so you fill out the 2p6 electrons. You have to get to iodine over here, so you have to fill all these electrons out. Okay, so then you go on to the 3s2, fill that, go on to the 3p6, fill that up, come down here to fill the 4s2. Now, since iodine is down here, you still need to fill this one out, which is the 3d10 electrons. Then you go on to the 4p and you fill out the 4p6, okay, electrons over here. Go on to the next shell and go on to 5s2, and iodine is coming right across here now on the 5th shell. So then we have the 4d electrons here, so that's 4d10, and now iodine is 1, 2, 3, 4, 5. It's the 5th column from the transition metals, so that is 5p5. Okay, so this is how easy it can be to fill out the electrons, even if you have many electrons to fill out, okay, provided you follow the rules. So here is our answer, And let me just go through this with you. This one here is written out according to what we just filled out in one line. But then I wrote this out so that you can see clearly how we went row by row. Okay, so 1s2 and then the second row, then the third one. In the fourth one, starting from 4s2, we did the 4s2, 3d10, 4p6, and then the fifth one, okay, over here. So this is how we filled it out row by row. And this is how you should learn how to do it because it is the easy way to do it. Let's look at some solved problems now for electronic configurations. You will get electronic configurations as well as box configurations from me, and then you have to figure out what is wrong with them, okay, and explain to me why things are not working for them. So here are three examples that we're going to work on, which is the 1s2, 2s1, 3p6, and then so on and so forth. So let's look at the first one. Okay, in the first case, we have 1s2, 2s1, 2p3. So what is wrong with this configuration? All right, and we start from looking at the 1s2, which is 2 electrons. Then we have 2s, which is 1 electron, but then we have p, which has 3. So p3 is fine, except that this should be filled up first. Okay, the s should be filled up before we can start filling up the p electrons. Okay, so s should be 2 over here, and then p will be 2. For the next one, we have 1s2, 2s2, fine, fine. But then when we get to P8, that's not possible because P can have only 6 electrons, all right? Okay, so now C is getting a little bit larger. So we have 1s2, 2s2, this is fine, this is all okay. 2p6 is also all right. 3s2 is fine, 3p6 is also okay. When we get to 3d11, well, that's not possible at so many levels, okay, for this one. So our answer here is, first of all, after 3p6, you should actually fill out 4s electrons, and then in D, you must have only 10 electrons. Yes, okay, so first of all, fill the S before D, and then D11 is not possible because you can have only 10 electrons, so you fill out to be 9, which we also know has to be an exception because D should be either 10 or 8, okay, not 9. So then our configuration is actually S1, D10. So yes, this was a little bit more complicated than the first two. Then let's get on to what is called the valence and core electrons. Valence electrons are the outermost electrons. Core electrons are inside. Outermost electron meaning in the outermost shell. The highest shell number, which is the N number. Okay, number 3 here is the highest one. So that is the valence electrons. Everything inside is the core. All right, so whatever has the highest principal number, okay, the main quantum number N, that number is the valence electrons. Okay, and so when you start filling out electrons later on with the D orbitals, then you know that for D we actually have to go inside and then come outside for P again. All right, and so those D are not counted as valence electrons. You only look at the higher number of the principal quantum number. So 4s2, 4p4, which means we have 6 valence electrons, okay, in case of selenium. We've also learned about valence electrons back in chapter 2 when we were doing bonding. Whatever group number you have, that's the valence electrons you will have. So if selenium is found in group number 6, it has 6 valence electrons. Silicon is found in group number 4, so it has 4 valence electrons. So technically it should not be that hard. However, in this chapter, or starting from this chapter, you also should be able to figure out exactly where those valence electrons are. Not only just how many they are, but they actually exist in S or p orbitals. And then there is something called noble gas configuration. Noble gas configurations are very useful when you get to really large number of electrons. Okay, so for example, we were filling out iodine, and iodine is humongous. Okay, 53 electrons was a lot to fill out, although it's very easy, okay, because all you have to do is follow the periodic table, but still it's a very large number of electrons to fill out. So what we do in that case is we look at the noble gas just before the element. Okay, so here is an example for bromine. In case of bromine, you have 35 electrons, and the noble gas coming after bromine is krypton. So you can't use krypton. You look at the noble gas before bromine, and that is argon. Okay, and so then you fill out argon and then the rest of the electrons after argon. Okay, so argon is the noble gas. Argon takes care of 18 electrons because argon has 18 electrons. So you don't have to fill out those 18 electrons, you fill out the rest of these electrons. Okay, so which means until over 3p6 is taken care of, the last three then you have to fill out. So that makes life a lot easier for us because then we don't have to fill out every single electron at every single level. Okay, and so you can use noble gas configuration pretty much for everything, but please, you have to note that unless the question is asking you for noble gas configuration, do not give the noble gas configuration. If you're asked to fill out the SPDF notation for anything, then you have to give it for the entire thing. All right, so bromine, this is the entire SPDF notation. This is the noble gas configuration. All right, so please read the question carefully as to what it is asking you. Okay, so one thing that you need to note over here in this case is for the noble gas is that D is still the core electrons. These are the valence electrons, 4 and 4. Okay, 4 shell, the fourth shell, so 2 plus 5, these are the valence electrons. D comes in core, but that's not the point for noble gases. Noble gases is that you take care of a certain number of electrons that are found in the noble gas. So for example, neon, argon, krypton, you can use those to fill out certain number of electrons. In case of ions, you have less or more electrons. Okay, so for example, if you have a cation, then electrons have been given away. The electrons go away from the higher energy level first. A higher energy level meaning valence electrons are given away first. All right. In case of anions, electrons are added, and electrons are added again in the valence shell. Everything happens in the valence shell. When we get to transition metals, then things will start happening in the core electrons, because for transition metals, all the electrons are in the core, right? They're not in the valence. So then you have to deal with the core electrons. But as far as for all the main group elements, the S block and the P block is concerned, you have to remove electrons from the outer shell and add electrons to the outer shell. Okay, so for example, if we have aluminum, and aluminum can give away 3 electrons, it will give away the valence electrons, which are the 3s2 and 3p1. So by the time you're writing the electronic configuration for Al3+, aluminum 3+, you will have 1s2, 2s2, 2p6 because 3 electrons have been given away. In case of anions, we have to add the electrons, and when you add the electrons, then remember that you're adding again to the valence shell. Okay, so for sulfur, for example, sulfur can take 2 electrons, so you will add them in the valence shell. Okay, whichever one is the highest energy level one then. So 1s2, 2s2, 2p6, that's all fine, 3s2, and then 3p4 is where the 2 electrons will come in. So when you write the electronic configuration now, 3p will have 6 electrons instead of the 4 because now you added the 2 electrons. Okay, so that's how you write the electronic configurations for ions. The last concept to talk about in this section is paramagnetism and diamagnetism. The paramagnetism and diamagnetism come from the fact that electrons have magnetic spin, as we talked about. And magnetic spin was how we paired up electrons. Remember, we were filling electrons singly first and then pairing them up in boxes. And so paramagnetism comes from the fact that electrons are unpaired. Okay, so if you fill singly the electrons in the boxes, then it means that those substances can be magnetized. Okay, so paramagnetism means that any element can be magnetized, and the only way they can be magnetized is if they have unpaired electrons, because remember, all the electrons are spinning in the same direction, so then they can be magnetized, just like the earth is also magnetized. Similarly, a diamagnetic substance has all paired electrons, and a diamagnetic substance cannot be magnetized. Okay, and that is why some elements, for example, like iron, can be easily magnetized. Okay, you can make great magnets, okay, using iron, but then some substances cannot be magnetized like tin because it has all paired electrons, and so tin cannot be magnetized. So that is a property that comes from the electron spin, okay, excuse me, the magnetic spin of any element, which is the MS number. If you want to read more about this, you can go to this site from your PowerPoints. Okay, the ChemWiki from UC Davis, it's a pretty good website, and it'll give you a lot more information. So finally, from this chapter, you should know how to do the SPDF notations, the box configurations, noble gas configurations, know the 3 rules as to how we fill it out. And yes, you have to know what is Hund's rule and what is Aufbau principle as they are. Of course, you're using them to fill these configurations, but you also have to know what each of these are. You have to know the paramagnetism, and you have to fill out the configurations of cations and anions and all sorts of configurations. That's this part of this chapter.